Let it go.
Oh, yeah? I'll wait for him outside. I'll take care of it. What are you gonna do? I don't want your taco.
Okay, the final exam is no more difficult than the study guide, and there'll probably be less questions on it. These would be the maximum amount of questions that would be there. There's going to be less. I know that's going to be disappointing for some of you, but you'll just have to live with it.
This is 40% of our grade?
No, only 30.
Okay.
40% of your grade is your homework.
Okay.
Yeah.
What bad idea.
Yeah, that was a bad idea not to do it all. Yeah, I know.
Now, do we know if we're in chapter 14?
Yes.
Okay.
Yeah, you still have chapter 14 homework.
And part of 15?
Part of 15, right.
Okay.
But only as far as I went. Well, I think you've seen this guy before, right? So it's, and I'm probably not going to mix it up, so it's probably even going to be in the same order. Charge, Coulomb, if I could spell Coulomb, C-O-U-L-O-M-B maybe. Voltage, a V, amps, an A, an omega, resistance. It might just be an empty thing and you have to put everything in, right? Could be that too. Capital S for Siemens, conductance. And what are these guys? I would go with EMF, so that's short and sweet, and current is flow of electrons, right? Flow, misspelled flow of electrons.
That looks like a mess.
Yeah, and resistance is futile. Wrong one. Yeah. Yeah, resistance currents for it. Resistance current flow.
What is that?
I don't know.
What is it? Resistance current flow?
All right. Well, I'll move everything over like that, and then I'll have enough room. That'd be better.
Better.
Yeah, I can see it now.
Okay, excellent.
I think it says fairness.
Yeah, it says something. Yeah, I don't know what it says. Okay, well, current is the change in charge. Charge is normally a Q, change in time. So that'd be 45 coulombs divided by 15 seconds, 3 amps. Okay, which should be used to measure volts. That one there. Now, clearly if the study guide is asking you volts, and the test is probably going to ask you amps, right? So don't be circling the volt one because it was on the study guide. That would not be very professional.
You need to change pants. That one is too fat.
I don't think I have a thinner one. No, right here. What are these guys?
There you go.
Oh, there we go.
That might help.
Now you're probably not going to like this one at all. Find the current in the circuit above. Oh, no circuit above, no problem. Let's see, V is equal to IR, and so current is going to be voltage divided by resistance, and now we got to go figure out what those guys are. 12 divided by 2K, 12 volts divided by 2K gives me 2 milliamps. I don't see that that's any different in size. I wonder why. Oh, what is this? This is line style. Yeah, I don't see that that's giving me any difference at all.
Yeah.
It'd be 6 milliamps.
Not 2.
Oh, I don't know. Just waiting for the front row to tell me I'm wrong.
Well, you were wrong, but you were figuring out
Somebody-
that's more important.
Is that better?
We just don't look.
A little bit, yeah.
Alright.
It was wrong, so I don't think that that's the right answer.
Yeah. Calculate the voltage. Alright, so V is equal to IR.
Because of Jesus.
2.5 K, 1,250 maybe? No, 12,500. So I would stick that right here. That probably won't be enough room to stick it right there, but that's where I'd stick it. I might circle this guy. That, of course, would be minus 0.1 because I don't have any units there, and I got volts. Now I'm okay now. I'm okay. It says volts. Another answer that would be perfectly okay would be 12.5 kilovolts. You could write it that way too if you'd like. If in fact you had an answer that big, which there's no guarantee, because the question will be identical, it's just the answer will be different. And if we're not calculating voltage, we are obviously we're going to have to calculate resistance. Now I got those stupid bubble thingies around, so but we don't have time to get rid of them. So if V is equal to IR, then resistance has to be voltage divided by current, which has to be 15 volts divided by 3.52 milliamps. And that is, of course, something that I probably can't do in my head. So I'd probably,
4.26 milliamps.
4.26 K. All right. 4.3 K would also be acceptable. I have 2 significant digits in the voltage, 3 in the amperage, so you could go 2 or 3, I wouldn't care. Unless, of course, you're Dustin, then I'd have to grade it differently then.
I missed it.
You missed the joke?
I did.
Oh, gotta wake up for the whole class, you know. Otherwise, you're just gonna go right by you. Now this takes a little more thought here. So power is voltage times resistance is I squared R is voltage squared divided by resistance. Those are all truisms. And voltage is equal to IR. So Ohm's law, our power equation, and an equal sign that doesn't look much like an equal sign. So if I had 1,500 watts, the first issue is the pairs of voltage, the possible pairs of voltage and resistance are infinite. So we want the easiest ones. So if I had 150 watts and I had 2 amps, then what would my voltage be? Well, my voltage would be 75 volts. Okay, the 2 goes into 150 and I got 75 volts. If I had 75 volts and I had 2 amps, what would my resistance be? If I had 75 volts is equal to 2 times R. Then my resistance would be half of that. 30 something? 30,
32.5.
huh?
32.5.
32.5, really? All right. I don't believe a word of it, but
No,
that's
it's
okay.
30. I don't think you listen to Brent. Well, that's 65.
37.
Yeah, 37.5.
Oh,
That's what I meant.
37.5. 37.5. Yeah. Yeah,
Yeah, I'm just a genius. You guys all have calculators.
I know. Okay, so there's a answer. Now we have half credit. Now the issue is, how am I going to get the second answer when there's an infinite number? Well, we'll just pick a different wattage. The 150 is a maximum, so that's a maximum. So I'll just pick something less than that, like 100. So if I had 100 watts and 2 amps, then that would imply that my voltage has to be 50 volts. And if I have 50 volts,
Oh, what? That's the answer.
Maybe you're screwed up.
all right, and I had 2 amps, then that would imply that I had 50 volts. And if I had 50 volts and I had 2 amps, then that would imply that my resistance would be 25 ohms. So there's my second pair. Now I can get the second pair by doing anything as long as I come down in my wattage. If I do it with 200 watts, then I get the wrong answer, because 150 is the maximum I can have. So, but I could do it at 75 watts, or I could do it at 1 watt, or I could do it at 100 milliwatts, whatever, So I could find an infinite number of them if I were that type of person. And that particular problem is an operational analysis problem you'll get later on in life. Okay, this is another give me problem. What's 22 plus 12?
34.
34K ohms. All right. So you put down 34 minus 0.1 units. You put down 30K ohms minus 0.1 significant digits. So I can always find some reason to take something off.
Put K ohms down.
If you K ohms minus 0.9 answer. Something like that. Yeah, so whatever. Yeah, I'll be. Yeah, you still get 0.1 credit for. Yeah, you still get 0.1 credit for that. All right.
Smart, dude. That's cool. Yeah, I don't know. Yeah, you guys lost me.
Okay, we got lost back up here. 22 plus 12, 34. I'm in kilo ohms.
No, I know how to get
KO.
the answer. I
Oh.
don't know how to give your explanation.
Well, these are the points I take off if you get it wrong.
If you just wrote down K ohms, you get minus 0.1, which means you still get 0.1 of a point. Just
Yeah, you get a tenth of a point for getting the right unit. Yeah.
So by putting the label K ohms, I get a point.
Yeah.
Point one.
Yeah,
And then if I
point
have
one.
the right answer, I get the 0.9.
Yeah.
Okay, I'm on board again.
Yeah, I know. It's difficult.
Well, with all these tests coming up, my mind is drained.
Okay, well, I need resistance total. If I don't have resistance total, I can't find current total. Without current total, I don't know the current. Without the current, I don't know the voltage. Without the voltage and the current, I don't know the power. So 1.5, 2.8, 3.46. 3.46 K ohms, maybe. All right, so now I know that. So now I have to find the current total, which is going to equal the current 1, which is equal to current 2, which is equal to current 3, because I am in series, and in series, the current has to be the same. So I got 25 volts divided by 3.46 K. And again, I can't do that guy in my head. I know I should be able to, but 25 divided by 3.46. 7.2. Yeah, that's probably good enough. I probably only have 2 significant digits, right? 7.2 milliamps. So I come up here and write 7.2 milliamps, 7.2 milliamps, 7.2 milliamps. All right, now I got 1/3 of it right already. So that's pretty cool. Then I'm going to go and say, well, was V equal to IR earlier in the game? Yes. It's still equal to IR now, even though I can't spell IR. Okay, so the voltage across the first resistor has to be that 7.2 milliamps times 1.5K. And the voltage across 2 has to be 7.2 milliamps times 1.3K. And the voltage across resistor 3 has to be 7.2 milliamps times 660 ohms. Okay, so now I take my calculator. Do I have to put keystrokes down for anybody for this one?
Yes, please.
11 volts. So I'm going to go 7.2 times 1.5 equals. I can drop the milli and the kilo because I don't need them. They're going to cancel each other out. And then I'm going to go 7.2 times 1.3. Nine point four volts. And then I'm going to go 7.2 times 0.66. I'm going to change the 600 to kilo so I don't have to put in milli. Four 4.7.
4.6. Otherwise, it doesn't add up.
Yeah.
Actually, 4.75.
It's 4.75. I'd go to 4.8, but if I go 4.8, then I'm going to be hosed. But I'll just be hosed. Doesn't matter. 4.8. And then 11. And 9.4. And then I add those guys up. I need to get to 25, and I get to 25.2. And I say, well, that's good enough. And so now I'm going to go, power is voltage times current. So I'm going to go 11 times 7.2. We'll call it 80. 80 milliwatts. 9.4 times 7.2. We'll call it 68 milliwatts. 4.8. Yeah, I am.
You have to?
Well, I only have two significant digits. Why would I want any more
But
than that?
if I don't round it, I'm still good, right? Making sure.
300. Now you got me all confused. I put the wrong number in my calculator. 34 milliwatts. So the question from the peanut gallery is, I go and I put, instead of putting 74 milliwatts, I put 74.56, 34 milliwatts. I put something like that down. I go minus 0.1 significant digits. Because you don't have 4 significant digits. You can't put that down.
Would 35 be okay?
35 would be okay. The normal Cordoville grounding rules say that if this is a 5 and that's even, I keep the even. If this is a 5 and that's odd, I round up. So that's the normal Cordoville rounding rules. But if you were taught, if your 8th grade math teacher taught you different rounding rules, then it wouldn't matter to me. I would not complain with 35 milliwatts. Of course, that's me, because I don't complain. Do I complain about anything?
No.
No. Other than, Rumundo needing a haircut, I mean, I complain about that all the time, right?
Tell me about that.
Yeah. About all that I complain about. Well, it looks like all I'm looking for is just resistance total on this one. So if I can get it into my other guy, that'd be okay. So I'm going to go 5, not in red though, 560, 1 over key, plus 650, 1 over key, plus 750, 1 over key, equals 1 over key, and then I'm going to write down the answer, and if my answer isn't less than the smallest one, then I know it's wrong and I have to do it again. Alright, so I've got 560, 1 over key, plus 650, 1 over key, plus 750, 1 over key, equals 1 over key, and 200, and I have 214.707039. So that's what I've got. So I look over here, 2, 2, 2. I only have 2 significant digits, 210 ohms. Now number 11, I hope I did something cool. No, I didn't. I figured I did something bad with number 11. I figured I was going to use 10 to solve number 11, but I'm not. Okay, so what do you think I ought to do first? You know, if I was in a better classroom, we could have you guys go to the board and solve the problem. Wouldn't that be better?
What?
Huh? If I was in a better classroom, you guys could go to the board and solve the problem for me. Okay, the first thing I need is what?
Resistance total.
Resistance total, correct. So resistance total is 3.7K in parallel with 2.5K plus 1.3K. So I go to my calculator. I'm going to be in K when I get done, so I can drop the K in my calculator altogether. 3.7, 1 over key, plus 2.5, 1 over key, equals 1 over key, plus 1.3 equals key, and then I'll write down what my resistance total is. And I got 2.79K, 2.79K ohms. So I'll call my answer 2.8K ohms. But I'm going to use 2.79 in my calculation the rest of the way through, and then I'm going to round down to only 2 significant digits in everything I do. Okay, so now I need to find current total, which is also the current across resistor 1. Okay, so that's going to be 65? It's going to be 65 volts divided by 2.79K. Alright, and I know my answer is going to be in milliamps because I have a K on the bottom. Alright, so I got, okay, so I'm going to go 1 over times 65, and I have 23.3 milliamps. So I'll come up here and write 23 milliamps because I only have two significant digits. Okay, I'm going to take my 23.3, I'm going to multiply it by 1.3K to find the voltage. So voltage 1, current 1, resistance 1, 3.2 milliamps times 1.3K. Okay, so I'm just going to go then I have 30.26 volts, but I'm only going to keep two significant digits, so I'll call it 30 volts. Okay, now if I have 30 volts, 65 total, I lose 30 here, that's going to leave me 35 left over. 35 volts, 35 volts. My current is voltage divided by resistance. 25 divided by 3.7, 9.4 milliamps. My voltage divided by resistance, 2.5, 14 milliamps. I add them together, I get 23.4, which is okay, because I have 23. And I'm going to multiply across to find power. Power is voltage times current. 30 times 23. 690 milliwatts. 35 times 9.4. 330 milliwatts. 35 times 14. 490 milliwatts. Okay. Notice how you get 1 point for every problem as you continue on with the test. So you still get 1 point, but you have to do more to get it. So that's one of those reasonable things. However I want to grade it is fine. Anybody object to that? If so, put it in writing on the top of your test, so I know who's complaining about it. Just in case. Oh, something happened. I didn't get it. Oh, there we go. This is a superposition problem. Okay, so that means I'm going to short out one of the batteries, find the current, and then I'm going to short out the other battery and find the current. Okay. So I'm going to go in short the 40 volt battery. Okay, if I do, then I'm only concerned about R1 here. I got a total resistance of 85 ohms. So my current through R1 is going to be 24 volts divided by 85 ohms. Grab my calculator. Um, 282 milliamps, and it's going to be flowing that way. 282 milliamps, because I'm positive here, it's going to go that way. Okay, now I'm going to short the 24 volt power supply, and I'm going to find the current through 1 is going to be 40 volts divided by, now this is shorted, so this guy's irrelevant over here, divided by the same 85. 40 divided by 85. 470 milliamps. I find that that is flowing that away, 470 milliamps. So now I found out the current through 1 has to be 470 minus 282 in milliamps. 470 minus 282, 188, so we'll call that 190 milliamps. Is there anything wrong with 0.19 amps? Well, that'd be a perfectly okay answer too, right? Okay, now that I know that it's 190 milliamps, I multiply that by 25 ohms. 25 times 0.19, and I come up with 4.75, so I would round that to 4.8 volts. Now, there are alternative ways to do the problem. Would you like me to do it in a different way? Or you don't want to be...
Both. You don't want to be host.
You want to see a different way, or you want to just stick with that way?
Let's do
One way.
One way, okay. Well, you don't know if it's simpler or not.
I'll just get confused.
If you had a TI-89 calculator, the other way would be much simpler, but that's beside the point. Okay, 12.
We don't have 13.
Yeah, we're doing 13 next. Okay, so resistance Thevenin occurs when I short out my voltages. When I do that, I have 3 resistors in parallel. 20 in parallel with 65 in parallel with 100. So I'm going to go 20, 1 over key, plus 65, 1 over key, plus 100, 1 over key, equals 1 over key. And I'm going to write down the answer, and that's going to be my resistance Thevenin, and it better be smaller than the smallest one. Uh, 13.2, but I probably have no more than 2 significant digits, so I'm going to call it 13 ohms. 13 ohms. Okay, then I need to find the voltage through R1, across R1, so I can subtract it from 100 volts so I can figure out what my voltage Thevenin is. So now I need the resistance looking from the battery, so that resistance total is going to be 120. 20 plus 65 in parallel with 100. Okay, so 65, 1 over key, plus 100, 1 over key equals 1 over key plus 20. 59.4 ohms. 59.4 ohms. So current total, 100 volts divided by 59.4 ohms. .68 amps. The voltage across 1 is going to be 20 times the current total. .7 volts, and then 100 minus 33.7 66.3 volts would be the voltage Thevenin, but I don't have that many significant digits, so I would go with 66. Okay. Now the next set of questions come from the FCC licensing exam, and when I have the option of using those questions, I do, so that when you see them again, you'll know that that's where they come from. But when you see things like that, that's what they're all about. A loop is a closed current path in a circuit.
True.
A node is a junction of two or more current paths.
True.
The loop current is not necessarily the actual current in the branch.
True.
False.
Stay in the bus.
So, back here, we have a loop current going that way of 2.8 milliamps. We have a loop current going this way of 4.7 milliamps. Neither of those is the actual current in the branch. The actual current in the branch is 0.19 amps, 190 milliamps. Okay. But yeah, that was a trick question. I agree. There's no doubt about it. Unlike magnetic poles attract, like magnetic poles repel.
True.
There's some pattern here. A permanent magnet is basically a coil of wire wound around a magnetic core. False. A sine wave is the only waveform that contains no harmonic, or all other waveforms are composed of a fundamental sine wave and harmonics of the related sine wave.
That one I'm officially don't think is true.
I'd say a true.
Let's say true and false.
I would say waveforms are circular.
Okay, so here we go. There's true, there's false. Okay, show of hands for true. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 for true. Show of hands for false. 1, 2, 3, 4, 5, 6, 7, 8. 8 for false. 8 for false. All right, so as an FCC licensing question, the answer is true. So if you see that in the FCC licensing test, the answer would be
The
true.
ones that said true,
Now-
please explain.
The problem is education is different than the FCC exam, is the only waveform. Isn't the cosine also the same thing? So the cosine's a waveform that's a fundamental without any harmonics. So why wouldn't that count, and why wouldn't the answer be false? Well, because in electronics, we consider the sine wave to be the sine wave. The cosine wave is just 90 degrees out of phase with the sine wave. It's the same wave. And so we wouldn't consider, we wouldn't overread the question to call it false based on a cosine wave also contains no harmonics. We wouldn't do that. But if I were a math instructor, if I was doing Fourier transforms, for example, then I would make an argument in my math class that this has to be a false thing. But as a technician thing, the answer is true. That's the way we would think about it. I know you don't want to know all that, but just the way it is. Someday you have to know something, right? Anything at all would be good. This is the same thing that I had before. How come? How come I don't have something different? All right.
False.
False. The polar form of a complex number consists of two parts. Very true. Magnitude and amplitude.
False.
Very false. Magnitude
It's
and
the same thing.
an angle, amplitude and angle, but not magnitude and amplitude. Convert the following complex number from polar form to rectangular form. Okay, so it's going to, x is going to be
It's gonna be B.
2500 cosine 45, minus 45. And y is going to be 250 sine minus 45. The answer has to be a fourth quadrant answer, so it can't be A and it can't be C, but it can be B or D. Those are our two possibilities. So now, what is 2500 times the cosine of minus 45? 1767. All right, so that makes it B.
Can you put how you did it on a calculator on there, if you don't mind, please?
2500 times 45 plus minus key, cosine key, equal key. I could also use my polar rectangular conversion thing in my calculator too if I wanted to do that. Add the following numbers. 30 and 25 is 55. So it can't be this one and it can't be that one. 10 minus 7 is 3. The answer is B. So when I have, when I'm in a rectangular form, I add the real numbers and I keep them together. I add the imaginary numbers and I keep them together. I'm all set. Find the total capacitance. Well, capacitance in parallel adds. So this is the same as 6 microfarad, 5 microfarad in series. Capacitance in series follows the 1 over rule. So we would go 6 1 over key plus 5 1 over key equals 1 over key, and get some answer that is smaller than 5. .727. So 2.7 microfarads would be okay. 3 microfarads would also be okay, either one of them. And probably 3 microfarads would be a better answer because I only have one lousy significant digit. 2.72 or 2.73 microfarads would not be okay. That would be the awesome minus 0.1 significant digit rule. Okay, 24. The voltage across the capacitor is equal to whatever the initial voltage is plus 63% of whatever the voltage difference is. So at what time after the switch is closed will that happen? Okay. And this is for every period. So my time, what's that time constant called? Anyway, it's RC. And so 500 ohms times 1 microfarad farad would be 0.5 milliseconds. Okay, so after 0.5 milliseconds, I have initial voltage plus 63% of the difference, which would be 100. So I'd be at 63 volts. I'm looking at going to 68. I'm not there yet. After another time constant, 1 millisecond, I'm going to be at 63 volts plus 63% of the difference. 100 minus 63 is 37 volts. Okay, so now I take my calculator, 63 plus 0.63 times 37, 86.31 volts. I want to go to 86, so answer 1 millisecond, and I'm going to be charged to 68 volts. And in the problems on all your other tests, we had huge numbers. We were fully charged. It wasn't an issue. I don't think the final is going to be that way. I think the final is going to require you to figure out how doing that process. Initial voltage plus 63% of whatever the difference is. Okay, we want the total impedance. Okay, so my inductance total is 5 millihenry plus 2 millihenry in parallel with 7 millihenry. So in my calculator, I'm going to go 2, 1 over key, plus 7, 1 over key, equals 1 over key, plus 5 equals key, and write down my answer. It won't be an answer, it's just an intermediate one. 2, 1 over, plus 7, 1 over, equals 1 over, plus 5. 6.55. 6.5 repeating millihenry. Okay, now the problem wants to know impedance. So the impedance Z is the same as X of L, which is 2 pi FL total. 2 pi, what's the frequency? 1,000 hertz times 6.5 repeating millihenry. And when I get done, I'm only going to have one lousy significant digit. Okay, one lousy significant digit is all I'm looking for. Okay, the 1 kilohertz cancel out the milli and the henry, so I can go 2 times pi, if I knew where pi was on my calculator, times 6.5 equals, and it's 6.5 repeating. I'm going to do it again. 2 times pi times 6.5555555. Okay, I got 41.18 ohms. Okay, but I only have one significant digit, so for my final answer, I'm going to call it 40 ohms. Okay, so we're on page 7 of 11. I guess we can go home, right? We don't have to finish the study guide, do we? I just thought maybe we didn't have to finish it, but
Well, we just continue to make the video and we'll hunt that home.
that might work. I guess we'll try to do 3 at the same time. All right. Of course, I can't see them because they're too small, but other than that, they're okay. All right. So the first guy, we need the turn ratio. Okay, so turns primary to turn secondary is the same as voltage primary divided by voltage secondary, which is going to be 25 divided by 0.25. So the turn ratio would be 100, or you could have it 100 to 1, or you could have it 100 to 1, or you could have it 100 to 1. Any one of those answers would be perfectly okay. And okay, problem number 2, the primary voltage. Okay, same formula. The turns primary, turns secondary is the voltage primary divided by the voltage secondary. So I've got 1 to 20 is equal to, I don't know, to 296.573. Okay, in this case, I have 6 significant digits. So voltage primary, 296.573 divided by 20. The 20 we would call a whole number, and we wouldn't say I only have 1 significant digit there. We could have as many as we want. 296.573 divided by 20. 14.8. 14.8286. 14.8.286 volts is how I would call that guy. At this point in the test, you've already missed something, so if you call it 14.8 volts, I probably count that right. It's only in Dustin's case would we have to have all 6 significant digits, assuming he didn't have anything wrong by then. Same thing with Steve. Steve might not have anything wrong by then either. We'd have to take something off at that point. You know, and Alex is the same way. He could be sitting there on 100 by number 28. We'd have to take something off. Find the secondary current. Primary turns divided by secondary turns is secondary current divided by primary current. Okay, so 1 to 5 is equal to what I'm looking for divided by 1.238. So current secondary, 1.238 divided by 5. Again, I would call that 4 significant digits in my answer. 1.238 divided by 5. So I call it 247.6 milliamps would be my secondary current. Yeah, that's one way to look at it. Okay, find the primary power. Well, power is VI, power is I squared R, power is voltage squared divided by R. I know the amperage and the resistance. So secondary power is equal to 0.6 squared times 1,000 which is 360 watts, which is primary power, because the power has to be the same primary and secondary. Not totally true. A transformer does have an efficiency. It might be 95%, it might be 85%, it might be 97%. Why bother you with such details when we're only in our first semester, right? But there will be a time when we'll have to worry about the efficiency of such thing. Find the impedance. Okay, so turns primary divided by turns secondary is the square root of impedance primary divided by the square root of impedance secondary. 2.5 to 1 is the square root of the impedance primary divided by the square root of 1,000. So the impedance primary is 6250 ohms. Right? Well, 6.5 squared. 6.5 squared, yeah. So 6.25 times 1,000, because I have to square both sides to get rid of the square root. Okay. So up to that point, you have not given me any problems. You've gotten them all right to there. So now it's my turn to give you a problem that you're going to miss, right? All right, so I need to find x sub c. 1 over 2 pi 100 hertz 2 microfarads equals 2 times pi times 100 times 2 double E minus 6 equals 1 over. So I've got 796 ohms, angle minus 90. I only have 2 significant digits, so I'm going to call this 800 ohms. 800 ohms, angle minus 90 degrees. But I'm going to use 796 in all my calculations, even though I'm going to call my final answer 800. And I'd put a bar above the 0 to indicate I have 2 significant digits in my answer. Or not, depending on how you look at it. Okay, now, that was stupid. Erase that. All right, that's only x of c. Now I've got to find the parallel resistance, and then I got to add it to the series resistance. All right, so I've got 1 over 750 plus 1 over 796, right? 796 angle minus 90, all 1 over. Plus, I'm going to add 250 when I get done. Okay, so that's what I'm doing. So 751 over is 1 over 0.0013 repeating plus 796 1 over 0.001256 angle 90 plus 250. Now I'm going to have to come up with the magnitude of the guy on the bottom. I'm going to use the Pythagorean theorem, take the square root of 0.0013 repeating squared plus 0.001256 squared, and I'm going to come up with the magnitude of what I have on the bottom. 1 over 0.0013333333 squared plus 0.001256 squared equals second function square root second function answer close parentheses. All right, so I've got 0.00183. We'll worry about the angle next. So my angle is the arctangent of the y component, 0.001256 divided by the x component, 1, 3 repeating. Okay, so I've got, well, in the meantime, I'm going to have to do this one over, guys, so I'll do this one over while I'm at it. So I've got 546 ohms, angle something. I'm trying to figure out what that angle is now. 0.001256 divided by 0.0013333333 equals, and I need the arc tangent of that. So it's going to be 40 minus 43.3 degrees, because this is going to be plus 43.3 degrees. Plus, I have to add in the 250 ohms that I have in series. Okay, now, I need to take this guy and turn him into an X and a Y component guy, and then I'm going to add it to 250. Okay, so I'm going to go 5, 4, 6 cosine minus 43.3, and I'm going to go 5, 4, 6 sine minus 43.3 J. Okay, so that's what I'm going to do. I don't even have the impedance yet, in case you're wondering. 546 times cosine 42.3. So I've got 404 plus 546 times sine 43.3, and this is going to be a minus sign, minus 374J plus 250. Okay, so I got 654 minus 374J. Okay, then this is my impedance, so I'm almost done. Impedance total. So now I'm going to change it to polar form. So I'm going to go 640, 654 squared plus 374 squared, and then I got to find an angle later. 654 squared plus 374 squared equals, and I want the square root of the answer, and I have 753. Well, I only have two significant digits, so I'm going to start 750 ohms angle. Okay, so theta is going to be the arctangent of minus 374 divided by 654, and that's going to be an absolute value, and this has to be a reference number, reference angle. Okay, so 374 divided by 654 equals, second function, this is an arctangent. Arctangent of the answer equals, boom. So I got 29.7 degrees. Now, if I am positive in the x guy and I'm negative here, this is going to be a fourth answer. So that's just going to be minus 29.7. So we're going to call it 30. We're going to give it a angle minus 30 degrees. So now we're ready to write the answer up here. 750 angle minus 30. Okay, now we want the voltage across the resistor. Okay, so now we're going to calculate current total, voltage divided by the impedance total. And we're going to use the RMS value, so I got 50 divided by 750 angle minus 30. 50 divided by 750, 67 milliamps. 67 milliamps, angle 30. Is that something we want? No, that's not what we want. Okay, what we want is voltage across resistor 1. Voltage across resistor 1, 250 ohms times total current, 670 milliamps, angle 30. Uh, 16.7, we'll call it 17 volts, angle 30. $17 volts, angle 30. Okay, now we want the voltage across the parallel path, so we're going to want 50 volts minus 17 volts, angle 30. So that's going to be 50 volts minus, we're going to go 17 cosine of 30, 14.7 plus 17 sine 30. Sine of 30 is a half, so that'd be 8.5 J. Okay, and now we're going to have 50 minus 17.5, 14.7, 35.3 minus 8.5 J volts. We're going to change that to a polar form. 5.3 squared plus 8.5 squared equals. Stupid calculator. Oh, that can't be right. 35.3 squared plus 8.5 squared equals 35.2 squared plus 8.5 squared equals. Okay, so I want the square root of 1311. 36.2. 36.2 angle. Okay, so I want the arctangent of the Y guy, minus 8.5 divided by 35.3. Arctangent of the answer, minus 13.5 degrees. And this is volts, right? Volts. So the voltage across the capacitor, 36.2 volts angle minus 13.5 degrees. And one could claim that I don't have that many significant digits. Now I want the current through the resistor. Okay, so current through resistor 2 is going to be the voltage across resistor 2 divided by the resistance. So I got 36.2 volts angle minus 13.5 divided by 750. 36.2 divided by 750, 48 milliamps. Angle minus 13.5. 48 milliamps angle minus 13.5 degrees. Well, that was easy enough done. I hope the other ones are just as hard.
What was the current again?
I have no idea. Okay, you ready? You all set with that?
Yes.
Somebody was paying attention sitting next to you. I find it hard to believe. All right, what type of filter? So we have low pass, high pass, whatever. At low frequencies, this guy is a open, so this is going to be a low pass filter. On the test, it's obviously going to be a high pass filter because I'm not going to have the same one, right? But at high frequencies, this guy is a short, so my signal would be going directly through that capacitor, and that's why it's a low pass filter. What is wrong? Well, I have 2K, right? And 2K into 10 volts ought to be 5 milliamps, and I have 10 milliamps. The voltage is correct across this guy. If he were open, 10 volts would be correct, but I wouldn't have any current flowing, right? So this guy is shorted. So I only have 1K in the circuit, total resistance, and the only way I can get that is if I short that guy. Okay, now what's wrong with the circuit? Well, my resistance total is 560 plus 390 plus 220. 560 plus 390 plus 220. 1170. And 12 divided by 1170 gives me 10.2 milliamps. 10.2 milliamps. This doesn't read 10.2 milliamps. So one of these guys is shorted. Okay, so I'm going to take 3.3 6, is that 6/8? 6, 4, and I'm going to divide it by 220, and I got 15. So this guy is correct. So it's one of these two guys that are hosing me over. So now, if I assume that R1 is shorted, and I take 290 plus 220, 610, and I take 12 and I divide it by 610, I get 19 milliamps. That's not what I have. So this guy's probably okay. This guy's probably shorted. Okay, I'm going to take 560 plus 220, 780. I'm going to take 12 divided by 780, and I'm going to get 15 milliamps, and that is correct. So we're correct in our assumption that that guy is shorted. Okay. Oh, okay, I know what happened. Well, that doesn't do me any good. All right, well, I got 1, 2, 3, 4 guys in parallel, right? So I'm going to have to figure out the resistance total. Resistance total. 220, 1 over, plus 330, 1 over, plus 220, 1 over, plus plus 560, 1 over equals 1 over. So I should have 71.9 71.9 ohms. 71.9 ohms. If I did, and I took 9 divided by 71.9, I would have 125 milliamps. Okay, so I should be seeing 125 milliamps, and I don't. Okay, well, if I take 9 and divide it by 220, I would have 41 milliamps by that guy, 41 milliamps by this guy. If I took 9 and I divided it by 330, I would have 27 milliamps by him. 9 divided by 560, I'd have 16 milliamps by him.
So they're all shorted?
Huh?
They're all shorted?
No, they're not all shorted. That's what I should have. How shy am I? 125 minus 84 is 41. Okay, so either he's open or he's open, right?
That one, first one's not open because it's showing 41.
This can't be open because I have current going through him. So that guy is open. If I was shorted, then I would have 100 million billion amps flowing through this short, waiting for my fuse to blow, right? So he's open. Right, so that's what I would do in that particular one. All right, now we get to the easy ones.
Ouch.
Okay, so I look at this guy, what's wrong? There's no current, there's no voltage, so my only choice is a secondary winding is open. That's my only choice, because I have current and I have voltage across this guy, so this guy has to be working right on the primary side. The secondary guy has to be wrong. All right, so I got a 2-to-1 ratio. I see that I have the right amps flowing on both sides of the circuit. I have the right amps, but I have wrong voltages. How is that possible? How can the transformer be showing the right current and the wrong voltage?
So AC.
So the answer is this meter is a DC voltmeter in an AC circuit. This is basically reading 0 volts here, is what it's doing, 0.059 microvolt. So that is a tricky one, but you've probably seen that in your labs where you failed to change your meter, right? And all your stupid meters are reading 0 and you can't figure out why. You've probably seen that already. Okay, we're in the middle one. This is the same as the one before, so this is just the same. And I might do that. I might have the same problem on 2 different pages just to hose you over, so you can miss the same one twice. And here we are, the last problem.
She does herself in the beginning.
Okay, I've got some 1K and 100 milli. These guys are not all that big of a resistance. But no current, no voltage is getting over to the other half. So there could be multiple things wrong with this guy. Okay, it could be that both the voltmeters are DC. Okay, you could come to that conclusion, or you could come to the conclusion that L1 is open. So you could come to the conclusion that both voltmeters are DC. That's not the case, but it could be. Or 2, you can come to the conclusion that L1 is open. Or you could come to the conclusion that the ground is open. You could come to that conclusion. Or you could come to the conclusion that the power supply is off. You could come to that conclusion too, right? So those are all the possible
answers would be right.
right. Any of those guys would be right. I mean, you could you got multiple possibilities here. You probably think of some other ones. This wire is open between this wire here is open there. I mean, there's a lot of other possibilities. Now, before you get away,